I'm your host, Nick Jikomis, and today I'm speaking with Dr. John Speakman. John is a professor. He splits his time between the UK at the University of Aberdeen and the Shenzhen Institute of Advanced Technology in China, where he actually called in from for this podcast. John's research has focused on energy balance, the genetic and environmental drivers of obesity, and energetic contributions to aging. So he thinks a lot about energy expenditure. How do animals burn energy when they're doing stuff and when they're at rest? Diet, and how diet affects metabolism. How changes in adiposity or fat accumulation are related to not just how much you're eating, but what specific macronutrients that you're eating, different fats, carbohydrates, protein. And he has a sort of zoological perspective, so he's really good at putting things in ecological or evolutionary contexts, thinking about things like species differences between, rodents, humans, etc. And we talked about the obesity epidemic. We talked about differences in the patterns of obesity that we're seeing in places like China today versus the US over the past few decades and what that might tell us. And we thought about a lot of his recent research in the context of thinking about human obesity. So if you're interested in diet, composition of diet, fat, protein, carbohydrate composition, if you're interested in the causes of obesity and what that has to do not just with food intake, but energy expenditure. This is a really interesting episode. I think John does some of the most fascinating research in this realm, so I had a lot of fun talking to him for about an hour. This episode is supported in part by Athletic Greens. Their main product, AG1, is a comprehensive and convenient daily nutrition product containing 75 vitamins, minerals, and whole food sourced ingredients with less than 1 gram of sugar per serving, no nasty chemicals or artificial anything. It's gluten and dairy free and compatible with paleo, vegan, vegetarian, and ketogenic diets. AG1 is a quick and convenient way to supplement your diet to help ensure your body is getting the nutrients it needs. It comes in powder form, and you can mix it in water and drink it, or you can put it into a smoothie or a shake or something like that. I mix it into water and drink it with the first meal of each day, and it's super convenient. If you go to athleticgreens.com/mindandmatter, Athletic Greens will give you a free 1-year supply of vitamin D and 5 free travel packs with your first purchase. Their vitamin D product comes in tincture form, so you just take 1 drop each day. A large fraction of the population is actually vitamin D deficient, especially in winter months when we get less sun exposure, and vitamin D is super important for the proper function of the immune system and for a variety of other things. And there's even evidence indicating that vitamin D deficiency is correlated with more severe cases of COVID-19 in those who get infected. Every time I go into the doctor each year for a checkup, I'm always told that vitamin D deficiency is very common and I should be supplementing on a daily basis. So visit athleticgreens.com/mindandmatter or click the link in the episode description. You'll get a free 1-year supply of vitamin D with your first purchase. Hey everyone, I want to take a minute to tell you about a really cool health monitoring device I've been using for several weeks. It's called Lumen, and it's a handheld, pocket-sized device with a sleek design. It measures CO2 levels in your breath, which allows their technology to determine the extent to which your body is burning fats versus carbohydrates. Lumen helps improve your metabolic flexibility, your body's efficiency in shifting between using fats and carbs. It improves your ability to burn fat, which decreases your hunger levels and makes your body less dependent on snacking, and it can increase your energy levels by helping you develop a high-functioning metabolism. I use this device in the morning, before bed, and after meals and workouts to track my metabolism. With just a couple weeks of use, I learned a lot about which foods were causing my body to burn mostly fat, mostly carbs, or both, as well as how long I need to fast each day to promote fat burning. Lumen is great for anyone looking to optimize their health for either weight loss or athletic performance. The easy-to-use app allows you to track your results together with what you're eating and how you're exercising, and it syncs with other devices like the Apple Watch. Click the link in the episode description to learn more and use the code MIND, M-I-N-D, in all capital letters to get $50 off your Lumen device today. And with that, here's my conversation with John Speakman.
Thanks. How are you?
I'm good. Where are you calling in from?
So I'm calling in from Shenzhen in China, which is, if people don't know locations in China, Shenzhen's on the mainland on the opposite side of the bay from Hong Kong. So it's way down in the south.
And can you give people a little bit of background in terms of what kind of scientist you are and what your research interests are?
Yeah, sure. So I started my career as a basic biologist, sort of evolutionary ecophysiologist. So I did a lot of work looking at the way animals respond to the environment, how they manage their energy, how they store energy, these sorts of things. So it became clear that I probably wasn't going to be able to raise enough research funding to keep those things going. But understanding energy balance and physiology of energy balance has two big implications. One is aging research, and the other one is obesity research. And so I started to sort of actively pursue those things and ended up working on both of them to some extent, and eventually evolved into working not only on laboratory animals, which are extremely convenient for studying these things, but also now doing studies on humans. So I've come along a sort of pretty long path. It's also been a pretty interesting path because I'm from the UK originally. I'm from Manchester, and I did my PhD in Scotland, and after my PhD, I went to do a postdoc at the University of Aberdeen. That postdoc led into a faculty position, so I then started just going up the ranks in a faculty position, lecturer, senior lecturer, professor. And then about 12, 13 years ago, I had this big dramatic change in my life that we decided we would open an extra lab in China. And so I then moved to Beijing with my wife and one of my kids. And we spent 10 years in Beijing, mostly doing work on obesity, but still having the lab running in Aberdeen, keeping the aging work going. And then during the pandemic in 2020, I moved from Beijing down to Shenzhen. And so I'm actually spread about all over the place at the moment because we still have a few people still in Beijing, and I still have the lab running in Aberdeen, and my main base is here in Shenzhen.
And in China, is there an increase in obesity similar to the patterns that we've seen in the US and the Western world, or are things very different over there in terms of those things?
So China is probably about 50 years behind the US in terms of the numbers of obese people, but there are two big differences between obesity in China and obesity in the US. So the first big difference is it's principally an issue in males rather than in both sexes. So Chinese women tend to be extremely culturally resistant to putting on weight, and that's maybe just a social pressure type thing. But you don't get enormously large women in China. And the other thing is it's spatially also very different. So the east coast of China, which is where most of the economic development has happened, has a much bigger problem with overweight and obesity than the Western provinces, which are more rural. They're also at higher altitude, and there is a link between altitude and obesity in the US. So whether it's a cultural difference or a development difference or an altitude difference is not really clear, but there is this large difference between the East Coast and the Western provinces.
Yeah, my understanding of the obesity epidemic in the US and the West is that one of the features it has is, people generally cite the late 70s or early 80s as being about the time that got started. But basically, it was indiscriminate. You saw it in males and females, young and old, rich and poor. To what extent is that true? And what do some of these demographic differences maybe start to tell us about where we should be looking in terms of causes?
Yeah, so that's pretty interesting. So one of the sort of rationales for the work I'm doing is, we're still at a very early phase of the epidemic here in China, and also if you look at other Asian countries as well, they're also very early in the epidemic. There's not much obesity. It's increasing in India, but it's not anywhere near in the US. And Southeast Asia is still almost completely protected. So one of the sort of rationales is that if we can work out what caused things in the US, then we may have a chance of preventing those things happening in Asia and Southeast Asia. So here it seems, though, that the patterns that are developing are very different than what happened in the US. So we do have these regional differences. We have these big sex differences. But on the other hand, there also seem to be some genetic physiological differences that the translation from obesity to diabetes seems to occur at much lower BMIs in Asian populations. And so although they have a much lower obesity problem, the diabetes problem in China is about the same kind of magnitude, same percent of the population have diabetes in China as they do in the US. And so that's also a kind of confusing but extremely interesting observation.
And you mentioned that interesting sex difference in terms of obesity rates between men and women in China. Are there any indications as to what may be driving that? Are women in China generally trying very hard to stay physically active? Are they trying very hard not to eat certain foods or anything like that?
I think there's a big social pressure not to become obese in women in China. And I think that manifests itself in various ways that they try and prevent weight gain, both by eating less and potentially exercising more. Although I personally think exercising more is not likely to be a successful strategy. But it certainly seems to work. I mean, there is a big difference. There are big social differences between females and males in China. So if you look at smoking rates, for example, the average smoking rate in China is about 25%, but in women it's 2%, and in men it's 51%. So there are enormous cultural differences and social differences between what men and women do in China that are not reflected in what goes on in the West. So I think it's not surprising that there are big sex differences in obesity rates.
Mm-hmm. Yeah, and we'll circle back to your comment on the role of physical activity in all this.
Yeah,
but
sure.
I want to set up some of the work that you've done recently. First, I just want to discuss obesity as an epidemic a little bit more. When we think about the causes here, there's obviously going to be multiple factors at play. But generally, you hear, the thing you probably hear about most is, well, it's about caloric intake because food is very plentiful. We've created and engineered many, many highly palatable, highly calorically dense foods, and we're simply eating more of these things. And that's, if not the biggest driver, certainly a big driver of this. But another factor here is just total energy expenditure, and that can come from both deciding to go do things like exercise. It could also come from changes in basal energy expenditure. And so can you unpack those concepts and maybe talk a little bit about sort of how the major schools of thought that have gone into thinking about the obesity epidemic thus far over the past few decades?
So I recently went to India, and when I arrived in India, I was questioned by the guy at immigration. So he's sitting behind the immigration desk, and he says to me, why you are here in India? And I said, oh, I'm here giving a talk at a conference. So he said, what's it about? So I said, it's about obesity. And he said, it's exercise. That's what it is. It's reductions in physical activity. That's what the cause is. And he could see I kind of drew breath, ready to sort of say, well, I don't think it is exercise that's causing it. And he immediately jumped in and said, and fast food as well. So I think most people are pretty convinced that it's both sides of the energy balance equation that have been impacted over time. And I think if you speak to anybody who's not an expert in the field, that would be the kind of view that it's a combination of changes in the food that we have available that have prompted us to eat more food, and changes in our behavior and particularly our physical activity that have reduced our total energy expenditure. So until recently, those were really the two major ideas, and I think for most people, those probably still are the two major ideas about what's happened. And, I mean, if you're online, you see a lot of stuff that people saying it's blindingly obvious, what's going on. Why do we need to study this anymore? So about 25 years ago, we decided to try and put some actual data on top of some of those ideas. So my interest is in measuring energy expenditure. And one problem is to measure energy expenditure of people free living. So what we're really interested in is not the energy expenditure of somebody lying on a bed with a metabolic hood on their head. We want to know what's the cost of going about your daily life, because that's what people hypothesize has changed. And in the 1980s, late 1980s, early 1990s, I was involved in development of a method. I didn't invent the method, but I was involved in refining the method for measuring people's energy expenditure when they're free living. So that's, you would think on the face of it that that's actually really difficult to do, because the way that it's normally done is you wear a mask or something like that that's over your face. It collects the gases that you're taking in and breathing out. And we measure from the differences in those gases how much oxygen you consume and how much CO2 you produce. And from those two, we can work out how much energy you're burning. Now, obviously, if you want to measure your energy expenditure of daily life, wearing a mask on your face is going to restrict to a large extent most of the things that you want to do. So we need another approach to it. And there was this really smart guy in the 1950s called Nathan Lifson at the University of Minnesota. And he came up with this idea that he made this primary observation that the isotopes in carbon dioxide are in equilibrium with the isotopes in water. So what that means is, let's say I gave you an isotope of oxygen 17 or oxygen 18, and I put that into the water in your body, because of these exchange reactions that happen, that oxygen would also go into the CO2 in your body. And so he came up with this idea that if you did that, if you got somebody to drink water with heavy oxygen in it, you could measure then the CO2 production, because you would be able to work out from the reduction in that oxygen 18 how much was getting lost through the CO2. But there's a problem, because the isotopic label is not only getting washed out of the body by the CO2, but it's also lost every time you lose some water. And so it's not possible just putting in oxygen 18 or oxygen 17 to work out what your CO2 production is. But the really smart idea was, well, okay, that water is also tracked by hydrogen. So maybe if we put in a label of hydrogen at the same time, we can use the difference in the elimination of the two isotopes to estimate what the CO2 production is. And he did some preliminary experiments with mice, very small sample sizes. And the reason that it was a problem doing these experiments, the idea was fantastic, but the isotopes were super expensive. And so he had to beg isotopes from Los Alamos in California to get enough isotope to just do one experiment on one mouse and show like proof of principle that it would work. In 1955, that was. And then he published another couple of papers later. But it never went anywhere just because it was too expensive a technique. And actually, he published a paper in the early 70s saying that this would never, ever be used on humans because it would cost about $10,000 to $15,000 per person to make a measurement. And he couldn't imagine any problem in 1970 that would be worth spending $15,000 per person on. And he's probably correct. I mean, we probably still wouldn't use the technique if it cost $15,000 per person. But the refinements that were made in the 1980s and 1990s brought that price down and down and down. And so now it's possible to do that for about $900 per person. It depends on the exact protocol that you use, but you can use that technique. And there is actually a company that does it commercially now. So if you want to measure your own energy expenditure, you can go to this company and they will, provide you the isotopes and you drink them, you provide a urine sample. So the beauty of this technique is that after you drink the isotopes, you take an initial sample after they've spread into your body in about 3 or 4 hours. And then you go about your daily life. You just do what you're doing. And then 14 days later, you take another sample, and the divergence of the isotopes tells you how much energy you've spent during that time period. So this is a very long way round to answering your question, but in the sort of early 2000s, around about 2005, there had been a lot of studies by then that had used this technique. And so I had a colleague in the Netherlands, Klaas Westerter, and I said to Klaas, look, you've probably done enough studies on humans that we could go to all your studies and just pull out all the control groups and look at the decline in energy expenditure over time, because there is objective evidence that physical activity has declined over time. So we just wanted to translate that into a number and say, has the decline in physical activity been enough to give us enough of a change in energy expenditure that could be an important causal factor, and how important is it relative to food intake? So that was the motivation for our initial thoughts on it. And so I went to Klaas's lab for a couple of weeks, and we pulled out all these control studies. And what we found, completely to our surprise, was there was absolutely no relationship whatsoever. So if you look between 1990 and 2005, there was no change in energy expenditure whatsoever, in the total energy expenditure. And that was just a real shock, because everybody expected physical activity levels have gone down. There is some data showing like work time physical activity has declined over time. So it was just like a real shocking result, and I think a lot of people just didn't believe it. They just thought, well, okay, it's one city in the Netherlands where there's not enormous levels of obesity, and maybe it's just it's just an anomaly, and it's not there. So wind forward a bit, and round about maybe about 8 years ago, 9 years ago, all the people that there's not many people can use this technique. It's probably about 10 people in the whole world run labs that can use this method. And we all happened to be at a conference in Japan. And we were sitting around afterwards in a sort of Q&A session, and somebody in the audience said, why don't you guys get all your data together and produce a big database? And after the meeting, we were sitting around in the bar, and we said, actually, that's a really good idea. We should do that. And so we went away, and we were pretty rubbish and naive about how to build databases. And so we had a couple of false starts. And it's really funny, because they're not things that you think about, but things like differences in the way that people write dates has an enormous impact on things. And we just said to people, what day did you do it? And so, like everybody from the US was using month, day, year. Everybody else was using, China, they use year, month, day. Europe, they use day, month, year. So that was causing all sorts of different issues. And there were lots of other things, people expressing CO2 production in liters per day, and some people using it in moles and things like that. So anyway, long story short, we finally got our act together, and we were able to pull together about 6,000 data items. And so we thought, that's a good sample to actually now go in and look in more detail, because this is across the whole of the US and Europe. So it's no longer restricted to just one city. It's a much bigger sample. And, we can look for those trends in energy expenditure.
So this database captures energy expenditure by using this doubly labeled water.
Yes, right.
And give me a clear sense for how exactly is this doubly labeled water administered to people, and how do you measure how much they're drinking and stuff?
Yeah. So what happens is you come into the lab. Uh, Typically, you would have been fasted overnight. And what we do is we give you a glass of water to drink. So the water is enriched in oxygen 18 and deuterium. These are stable isotopes, completely safe. There's no risk. They already exist in your body at a baseline level. And all we're doing is pushing that baseline level up a little bit. So, for example, in your body at the moment, you have 2,000 parts per million oxygen 18. When we do the technique, we push that up to about 2,200. So there's no physiological impact and there's no chemical impact of the dose that we give you. But it takes time for that dose to be absorbed by your gut and spread into the water in your body. And so we then wait for a period of about 3 to 4 hours. And after about 2 hours, we get you to urinate to get rid of anything that's in your bladder at that point. And then at about 3 to 4 hours, you take another urine sample and normally take about 5 mils, but actually it only takes about 50 microliters to do the measurement. So then we take that sample and different people use different techniques. So some people just let people go and they come back 14 days later. We actually get people to take a sample every morning. So they take 14 samples through the time course, but it's very non-invasive. You're just, everybody sort of goes for a pee in the morning. So you just take a sample of your pee and put it in a tube. Most people are kind of happy putting it in the freezer. And there are some people who are not so happy with doing that, but generally it's okay. We can get people who are keen on doing this, and then we fit curves to those isotope eliminations in order to estimate how quickly the deuterium and the oxygen 18 are coming out. So it's not an invasive technique in any shape or form.
I see. So based on how these isotopes are exchanged between water and carbon dioxide, based on how quickly the body's eliminating them, it's going to give you a readout of what their total energy expenditure is.
That's right. That's right. So validation studies have been done by putting people into metabolic chambers for periods of about 7 days, where we can actually measure their gas exchange, and then we can compare that directly to the measurements using the isotopes. And those validation studies have been done continuously since the 1990s. So one interesting thing is that different people came up with different equations for how to calculate the energy expenditure. And those different equations were all in these different studies that were brought together. So one benefit of the database was that we were then able to recalculate everybody's energy expenditure using a single common equation. And we showed that that single equation performs best if you pull together all the validation studies. So it was a kind of nice thing to do, pulling the database together, because it allowed us to harmonize a lot of things. And so now everybody that uses the technique uses this new equation that we derived. And so we don't have to sort of correct everything back to the sort of new equation. So we ended up with these 6,000 measurements that go back to 1991 and come forward to about 2017, just before the pandemic. And we looked at what happened with energy expenditure. And actually, if you look at the data, if you just like throw the data on the page, then there's no relationship. There's no relationship between energy expenditure through time. But there's a problem. And the problem is that although we're randomly sampling people through time, of course, through time, people are getting bigger. So if you look at the average weight in 2017, it's quite a bit higher than the average weight in 1991. So not only did we have no relationship, but we had a problem because people were getting slightly heavier, and you would actually expect that their expenditure would be getting slightly higher because bigger people expend more energy than lighter people.
Is that just because they have to do more work to move their body around?
No, it's principally because they have more metabolizing tissue. So if you look at anybody in relationship to their body size, there's a positive relationship between the fat-free mass and the total body weight. So when people deposit fat mass, they don't deposit only fat mass. They also deposit some lean tissue as well. And so the consequence, and it's the lean tissue where most of the metabolism is happening. There is some metabolism in the fat tissue as well. But the consequence is that if you look across a group of people that differ in their body weight, energy expenditure is higher in the people that are heavier. And so you have to take that away so that through time, you're asking the question, if we took a person who was 70 kilos through that whole time period, how would their energy expenditure change? Rather than saying, okay, in 1990, we've got a 70 kilogram person. In 2017, we've got an 80 kilogram person. And when you do that, it turns out that there is a relationship, there's a negative relationship in both males and females in the adjusted energy expenditure. So that's the energy expenditure taking away this change in body weight through time.
I see. So going back to the 80s or 90s forward until just a few years ago, by this measurement, you're saying that people, the weight adjusted energy expenditure has actually gone down.
Yes. And that contrasted what we found previously in Maastricht, where we found that it didn't matter if you took the total energy expenditure or you took the weight adjusted energy expenditure. You can do various other statistical tricks with the data. It didn't matter in that data how you did it, it was flat. Whereas in the new data, when you look at the large amount of data that we have, there was a positive trend in body weight, so we had to remove that. And when you remove that, there was a reduction in total energy expenditure. So the initial thought was, okay, well, that's it. That's showing that there's a reduction in physical activity energy expenditure, and so physical activity is probably a cause. But of course, total energy expenditure consists of several different things. And so it's not quite so easy just to leap in and say, okay, the total's gone down, therefore it must be the physical activity that's gone down. And so if you look at, okay, what do you spend energy on? What's your total energy expenditure consist of? And it consists of four things. One of which we generally ignore, which may or may not be an issue, but I'm just going to ignore it because we always do so, and that's the energy cost of thermoregulation. So generally, we assume that individuals move around in habitats and they change the places where they live so that they don't have to pay energy costs of thermoregulation. So we have some evidence that that's probably correct, at least in the US, because if you look at energy expenditure in relation to latitude or differences between summer and winter, there's nothing. So people in Alaska spend about the same amount of energy as people in Louisiana. And it doesn't matter that Louisiana is 40 degrees warmer, centigrade. So basically we modify our environment. We use air conditioning to cool ourselves down. We use heating to warm ourselves up. And the environment we're in is approximately constant. And so there isn't a big thermoregulation effect. That may not be true outside the US. We only have data inside the US. But generally, people ignore thermoregulation. And our data tends to suggest that's an appropriate thing to do. So that leaves three things that are left. So one's obviously physical activity. We spoke about that a bit so far. But there are two other things. One's called the thermic effect of food. And it has various other names like the heat increment of feeding or specific dynamic action. They're all basically the same thing. And that's the observation that if you eat some food, afterwards there's a slight increase in your metabolic rate that lasts for a couple of hours and then subsides. And so that works out to be around about 8% of the food that you eat. And it depends on the composition of the food. So if you've got more protein, you tend to burn off a little bit more. But we can subtract that off by saying, well, okay, the total energy expenditure must on average be balanced by what's being eaten. So we can just take 10% or 8% off the total, and that takes account of the thermic effect of food. So then there's only one other component, and that's the basal metabolism. So that's how much energy you spend when you're completely lying at rest and not doing anything. And we can measure that directly using a hood calorimeter. So it's like mask on your face that's collecting your respiratory gases. And so since you only have two components there, you have the activity metabolic rate and you have the basal metabolic rate, you can kind of calculate the energy expenditure on activity by difference. So we have the total, we have the basal that we can measure, and by subtracting the basal from the total, we get how much is being spent on physical activity.
I see.
Now, it turned out from those 8,000, from those 6,000 data, we only had basal metabolism measurements for about 1,400, something like that. But that allowed us to directly calculate what the activity energy expenditure was, so we could then show that the total reduction was due to the activity reduction. And much to our surprise, it turned out not to be the case. That actually energy expenditure on physical activity has actually gone up slightly.
Since when?
Since the 1990s.
Okay.
And energy expended on basal metabolism has actually declined. And so the decline in the total is principally because the energy cost of just lying down at rest is lower now than it was 30 years ago, which is completely unexpected. And because people didn't expect that until we kind of published this paper in 2022, nobody had suggested that changes in basal metabolism were a potential driver for the obesity epidemic. But now we have this new kid on the block sort of thing that basal metabolism could be a potential obesity driver. And we were interested in, how the problem with the double labeled water technique is the first time it was ever used in humans was 1981. And there was very little data through the 1980s. So we don't really have any good data before early 90s. And so, of course, people look at that and they sort of say, yeah, but the problem with the obesity thing started in the 1960s, 1970s. So we were interested in whether basal metabolism had only gone down recently, since the 1990s, or whether there's a longer trend. And so what we did was a big literature review where we pulled out all the measurements that had been made in the US and Europe. I should point out that the analysis that we did on the total energy expenditure is restricted to the US and Europe, where there's been an obesity epidemic. And so we went right back to the 1920s when the initial first good measurements were being made of basal metabolism. And that trend, it's there through time, all the way from 1920s right through to the modern day.
So yeah, I mean, this is sort of puzzling at first glance. It's been going down since.
It's not only puzzling at first glance; it's puzzling all the time.
So in principle, what could be the causes for a decrease in basal metabolic rate? What kinds of factors would make an animal's basal metabolic rate go down?
So there are a few sort of things that are potentially important. So one of the main features that we think is potentially important in explaining the difference in metabolic. If you have two people that are the same total weight, same fat to lean ratio, but one of them has a higher metabolic rate than the other one, then there are several kind of potential explanatory factors. So when we've looked at animals, it seems to depend to some extent on the sizes of different organs. So if we look back at some work we did like 20 years ago in mice, we measured the metabolic rates and then we chopped them into pieces and looked at the sizes of the different organs. And it turned out liver size was one of the main things that influences this variation once you take out total body weight and composition. So it is theoretically possible that there's been a reduction in the size of these metabolically active organs over time, and that accounts for the changes. Seems unlikely, but we're never going to be able to check it because the data is not there in order to test whether people in the 1920s and 1950s had bigger livers than we have now. The next main thing is hormonal effects. So one of the main things that influences your metabolic rate is, for example, levels of thyroid hormone. So we know that that's important. We know it's important in humans. But again, we don't have good data on whether there have been trends in thyroid hormone or any reason to suspect why there might have been changes in thyroid hormone through time. But that's another kind of possibility. And then we're into a sort of gray area of, okay, well, what's left? Once you've accounted for the organ sizes and you've accounted for the hormones, what else is in there? And one potential thing that has changed over time is diet. And so I mentioned that the thermic effect of food, for example, depends on what you eat. So when you eat more protein, you get a sort of stimulation of your energy expenditure. So maybe your basal metabolism, even though it's measured when you're not eating and you're what's called post-absorptive, it could be that your general habits in terms of what you eat could affect your metabolic rate. So there is another thing as well. The other potential thing there is things like your immune system. So it could be, for example, that our immune systems were maybe primed to fight off all the diseases that were going around in the 1900s. And that as we eliminated the risk of disease and infection, our immune systems didn't need to be as good or as active. And what happened then was we just started switching off that system. So it will be really interesting to see what happens post-pandemic, but we don't have to have that data yet. But the idea would be that you would decline your immune system, the cost of running your protection against disease, and that might be related to the reduction in basal metabolism. So that's a kind of interesting idea, and there is a bit of data that might support that. So a guy called Sam Erlacher has done some work on kids in South America that are in rural tribes, the Tsimane tribe, and looked at basal metabolic rates of individuals that are living out a rural lifestyle where they're exposed to lots of diseases and things like that, compared to ones that have moved into cities where they're then pretty much protected. And what he shows is that kids who make that transition get a reduction in their metabolic rate. So that's an interesting observation, but not necessarily there could be lots of things that cause that, not only, like a diet shift, for example. So it's not only the immune system that's changing. And in fact, there is other data. So for example, we did some work with animals in the wild where we dosed them with anti-parasite drugs. And what we found actually was when you removed the need to have an immune system because they didn't have any parasites and we eliminated them all, actually the metabolism went up. So, it's pretty confusing what's going on there with the immune system. And also, I don't think there were very big differences. There may have been differences between the 1920s and the 2020s, but I don't think there's big differences in
the 1990s versus today.
Yeah, exactly. Over the time course that we observed the decline in our data. So it seems unlikely that that's important.
Yeah.
So the big thing we're left with is diet.
Yes. And you did some experiments in mice that were really interesting,
That's right. So maybe we should just think about what's changed in the diet first. So if you think back to the 1920s, 1930s, so what's happened through time is there's been a big reduction in the amount of fat that we eat. In a big increase in the amount of fat that we eat. So there's been a change that we've slowly increased the amount of fat. We've also increased the amount of sugar that we eat. But the biggest change is probably the calories we're deriving from fat. But it's not a constant composition of fat. So what's happened is, at the same time that we've increased the total, we've actually reduced the proportion of that total that's saturated fat.
Mm.
So in the 1920s, we were probably 90% of our calories in fat were coming from saturated fats that are coming from butter and lard and things like that. In the 1930s to 50s, we got this takeoff in unsaturated fat, principally coming from sort of seed oils. And that has now grown to really dominate our intake. And so now the saturated fats are only about 16% of the total. And so we were interested in whether those shifts in the fatty acid content of the fats that are eaten could be an important driver of the metabolic rate. And we actually have.
And if I heard you right, that's quite a remarkable shift. You go from 90% of the calories of fat coming from saturated fat at the beginning of the 20th century down to, below 20% today.
Yes, that's right. So it is an enormous change. And but it's overlaid on the background of the total is going up as well.
Okay.
So actually, if you look at the actual amount of saturated fat that's being eaten, it's declined, but not anywhere near as much as that percentage suggests. So we're not going from eating like 90 pounds of lard a year to 16. It's a much smaller effect, but percentage-wise, that's what's happening. And most of that extra that we're eating is mostly polyunsaturated fat, principally linoleic acid. So there is that big move. And so what we were interested in is whether...
Sorry, before we go forward, the linoleic acid piece, is that primarily coming from is the driver of that change because we came up with ways to mass produce things like vegetable oils and they just became cheap and easy to get?
Yeah, principally. But also there was, of course, a sort of a health drive as well going on. So it wasn't just availability. It was that people were told that eating saturated fat is not good in terms of heart disease, and that limiting your saturated fat intake is probably a good idea. So there was a sort of shift towards, away from butter to margarine. Those sorts of things were happening through the 1960s and 1970s. It's interesting, though, that, we might think that, that was all driven from the sort of work that was done in the 1950s. But if you look at the data, the decline in the percent of fat that's coming from butter and lard, it starts much earlier. It starts in the 1910s, 1920s. And we're not really clear why that is, but it was already happening. It wasn't just like, Ansel Keys came along and said, look, it's really bad eating butter, and people stopped eating it. It was a gradual trend that, in fact, there was no acceleration during that time period, that it just continued on that same sort of trend, and we increased all these alternative sources. And they're kind of also a lot of hidden fats in food, because we use those in processed foods and things like that. So we did this mouse experiment. So one reason to do a mouse experiment is because it's very easy to control what they eat. So the problem with working on humans is you can tell them what to eat, but they have a choice to go away and eat it or not eat it. Mm-hmm. And so you never really know when they come back into the lab whether, the experiment worked or not, unless you keep them captive for a long time. But a mouse you can keep captive.
Yeah. I would imagine as well that for some of these diet-induced changes in metabolism, they probably don't happen overnight. They might require extended periods.
Right. Yeah, right. So when we did the mouse experiment, actually the mouse experiment was done by some guys at Yale, and they did an experiment that's about 3 months long. So it's equivalent to about 11 years in a human. So it's a good amount of time. So if there are changes going to happen, then you expect to see them. And what they found was that the change in the metabolic rate was mostly related to palmitate. So palmitate's a saturated fat. It's the biggest component in butter and lard. It's palmitic acid. So that was pretty interesting because that's the thing that's relatively gone down over time. And so it was consistent. These changes that we observed in the mice were consistent with the change through time in the human diet and the slow decline in the metabolic rate through time. So it was kind of all fitting together.
Okay, so higher intake in mice of the saturated fat correlated with more energy expenditure.
Yes. And higher intakes of polyunsaturated fat in general, but the major amount of that was linoleic acid, which is also the major component in the human diet. They were correlated with lower metabolic rate. So there have been some studies in humans that have tried to look at this, and they paint a sort of fairly mixed picture. So there are some intervention studies lasting a couple of weeks that suggest maybe there's an increase in relationship to linoleic acid intake. There's some other studies that suggest there's no change, but it may be just the study's not long enough, so it's difficult to tell. In terms of the mice, we'd actually already done a study in 2007 in my own lab where we fed mice different diets with different fat proportions, and we looked for the relationship between individual variability in fatty acid composition of the membranes of the livers and what the metabolic rate was. And we showed that palmitate was in the liver was a major driver of metabolic rate in the same direction as what we found in the other study.
Interesting. So more saturated fat, specifically palmitate, more energy expenditure.
So that's what we found in the mice. And at the moment, we're sort of designing experiments to see cross-sectionally whether that's true in humans. So if we can look at human diets and find out what people have been eating, measure their metabolism, see whether there's a correlation there, and then try and do some intervention studies. But it may be difficult just doing intervention studies that are kind of long enough.
Mm-hmm. And so from the 90s to the present, basically, the period of time that you have data with your doubly labeled water experiments, those experiments, again, they showed a decrease in total energy expenditure, which you just told us is mainly coming from a decrease in basal expenditure. Do we know anything?
Only coming from a decrease in basal. Yeah, because activity expenditure seems to be actually going up slightly.
Yeah. So it's gone down. Total has gone down despite that because there's been such a drop in basal expenditure.
Yeah.
Over that period of time, do we have good data anywhere
Sorry,
on?
I'm going to cough here. Yeah. Okay.
Do we have data on total caloric intake? Like, are we actually eating more calories per day today than we were in the 90s?
Yeah, good question. So I think that's extremely difficult to answer. I mean, the problem is measuring food intake is incredibly difficult. And the tools that we have available to do that are not really good enough to answer the question. So there was a paper recently suggesting that actually intake has been pretty flat through time for the last 20, 30 years. I'm not convinced that that's correct. If you look at food supply into the population, that's definitely gone up. And so either the waste levels have gone through the roof or we're consuming that food. And I think it's probably a combination of both. We're probably wasting more, but I think on balance, we probably are eating significantly more calories than we were 30 years ago.
So in other words, if that is true, that would obviously mean it's possible for a population to simultaneously decrease their baseline energy expenditure and consume more calories.
Yeah, absolutely. And I think probably the major factor driving the obesity is probably that increase in the food intake rather than the reduction in the basal metabolism. So the reduction in the basal may contribute, but I don't think it's the primary driver.
Mm-hmm. So another thing I want to ask you about here, this has to do with the topic of feeding behavior and the causes of things like weight gain and obesity. It's something I've talked about in the podcast before, which is fairly well known in this research world, which is the so-called protein leverage hypothesis.
Uh-huh.
So could you summarize what that is for people and what your take on that is and whether or not humans are or might be a protein leverage species?
Yeah. So the idea is a really neat idea that was produced by this guy Steve Simpson and David Robenheimer. So Steve is originally from the UK, but works in no, maybe he's originally Australian actually, and he was working in the UK. And he went back to Australia, but whatever. He's in Sydney at the moment, and they worked principally on insects looking at what regulates food intake in locusts, and they came up with this really cool idea. So the idea is that the mindset of everybody, including me, is that we eat food for energy. You know, the reason that you go out and you eat some food is to get the energy that's in that food. And people think that there's a regulatory system potentially in our brains that clocks how many calories we're consuming and matches that off against how many calories we're expending. And so we can adjust those two together. And what goes wrong in the obesity epidemic is that ability to match. And that may be undermined by the composition of the diet or whatever. So that's the way most people think about it in the field. But what Steve and David came up with was a completely different idea. And that is we don't eat food for its energy content. Actually, what we eat food for is its protein content. So if you imagine a situation, let's imagine you're feeding on a diet that's 15% protein and you're getting your protein needs from that diet. But suddenly you then get a diet that's only got 5% protein. So in order to meet your protein needs, you would have to eat 3 times the amount of that food. And that would give you a problem because if it's got the same calorie content of the food that's got 15% protein, and you've got to eat 3 times the number of calories in order to get that same amount. And what you can see is that that's not an enormous shift. 15 down to 5 is leading to a 300% change in the food intake. And so it may be that much more subtle changes, from like 15 down to 30, may be enough to drive the intake up, enough to create an obesity epidemic. And so that is I think, a really, really cool idea. That was called the protein leverage hypothesis, because what it's suggesting is that the protein leverages your energy intake, and that's what causes the obesity epidemic. So these small changes. I was really taken with that idea. We did a big experiment in mice about 10 years ago where we fed mice on diets with very different protein levels going from 30% down to 5%. And disappointingly, it provided absolutely no support for the idea at all. So certainly in mice, what seems to be happening is they eat for energy. They're eating the food to get its energy. And if you reduce the protein content, they just end up with less protein coming into the system. They don't adjust in any way for that reduction in protein. So that was slightly disappointing. Whether that's also true for humans or not, I'm not really sure. And whether we could actually detect the slight reduction in protein intake that would be necessary to drive that increased expenditure causing the obesity epidemic, I'm not sure we can even measure that. So I think it's still an open question whether protein leverage is an important factor in humans and the obesity epidemic. But as far as I'm concerned, in mice, it's pretty much not important.
Mm-hmm. And do you think that is, if we think about this in sort of ecological or evolutionary terms, do you think it's plausible that, some species, depending on the niches that they're adapted to, might be strongly protein leveraged, others might be weakly protein leveraged, others might be fat leveraged, and so on and so forth. And perhaps that's why an organism like a mouse, you don't see the results that you were expecting there.
Yeah, so I think, that's an interesting idea. The interesting thing is there are some studies that suggest protein leverage is important in mice. And if you look at the difference between those studies and our studies, the primary thing seems to be age. And so if you take a young mouse that's growing then it seems protein's really important for that mouse. And you can imagine why, because it's trying to build up how much muscle it has and all its lean tissue. So it needs protein to do that. And so protein leverage seems to be important during that growth phase. But once they become adult, which is the ones that we were studying, there's no effect. And so I could imagine that could be a general principle. The protein leverage is very important for animals during the growth phase, but not important when, once they become adult. If you read Steve's book on protein leverage, then he has some other examples in there that are kind of nice ecological examples of animals that go through seasonal shifts in the amount of protein that's available to them. And the consequence of that is that they, at different times of year, become enormously fat because they're trying to get protein from a resource that suddenly declined. But then when that goes up again, they lose all the weight during the summer. So they're not ratcheted up all the time. So I think there are some convincing kind of examples where it might be important.
And is there any clear indication that in the U.S. over time, the percent calories coming from protein has declined or anything like that?
So if you look at it, it's like spectacularly flat. If you look at what percent of protein, what percent of calories are coming from protein, but actually you don't need a big change for it to be important, and we can't distinguish it accurately enough to tell whether there's been enough of a change. So it's just not an answerable question with the data that we have.
Mm-hmm. And in those experiments where you guys, the experiments you did in mice, where you showed that dietary fat, but not protein or carbohydrates, was the primary driver of adiposity, of gaining weight, gaining fat.
Yeah.
Can you talk a little bit more about the results there, and in particular, the specific fat content? Was it mainly one type of fat, like saturated fat or unsaturated fat?
Yeah, right. So what we did was we came into that experiment wanting to change protein, fat, carbohydrate content. So we designed a matrix of about 30 diets where we could shift those contents. And the initial idea was to base those diets on some commercially available diets from research diets that are very widely used. But the problem with those diets is that as they ramp up the fat content, they change the fat composition. And that wasn't particularly good. So what we did was we designed a new set of diets that had a saturated to unsaturated ratio and a omega-6 to omega-3 ratio that matched the American standard diet. So we fix that in every diet according to what it's.
I see.
And
what are those ratios?
So if you look at like 6 to 3, it's about 14 to 1. And the saturated to monounsaturated to polyunsaturated, I think it's about 47 something. I can't remember what the mono and polyunsaturated are, but about half the diet in the data that we looked at was coming from. It depends if you do it by energy or weight. So, but if you do it by energy, it turns out it's about 47%. So we had those different ratios in the diet that match the American standard diet. And then we changed the percent fat in the diet and the protein and the carbohydrate. So what we got was a kind of interesting result that as the fat content went up, the mice got fatter, but it wasn't a linear relationship. So what happened was it kind of went up, and then at about 40%, it flattened off. And actually, as you went above 60%, it started to decline again. So actually, since we did that, so the paper we wrote said that, dietary fat is the only thing that makes mice fat. But actually, we got a lot of kickback then from the low carb people because they were saying like, oh, well, you didn't take the fat level high enough, you didn't take the carbs. So we've actually done now another 6 diets where we've taken the carbs right down to 0. And sure enough, it's a peaked relationship. So what happens is, as you increase the fat in the diet up to 40%, there's an increase in how fat they get. 40 to 60 is pretty flat. And then above 60, it just goes back down again. So once you're up to like 95% of the calories are coming from fat, there's virtually no carbs around, then it's back down to where it was at the beginning.
So that would be
So
like a ketogenic diet.
yeah, so actually, it's very difficult to push mice into ketogenesis because they can make glucose really easily, unlike humans. So they're not called ketogenic diets, but if they were fed to humans, they would be ketogenic. So the interesting thing is then it's like there's like a diet that is uniquely horrible. So that's where you get like 40 to 60% of your calories from fat. You're getting about 10 to 20% from protein, and the rest is carbohydrate. So what happens is if you're on that peak, that's probably the peak that is most rewarding to eat.
Mm.
And there's some recent stuff in humans suggesting that when we looked in the brains of the mice, what's lit up is all the reward areas in the brain. So when they're eating those diets, they're getting rewarded for doing that, and they're nice to eat. And you know, that corresponds to like pizzas, Oreos, ice cream, all the things that people eat and they get fat when they're eating. So the thing is, when you come off the peak of that mountain, you can come off it in two directions. You can come off it by reducing carbs and you reduce your body weight. And all those people say, what makes you fat is eating carbs. Or you can come off it the other way by going to a low-fat diet. And all those people say is what makes you fat is eating fat. But actually, it's both. It's the combination of the two that's uniquely fattening. So the interesting thing I kind of thought was, well, okay, why? Why are we wired up that way? Why are we wired to eat these foods? Because actually, if you look in nature, then those foods don't exist. You know, so most foods that exist out there are either plant-based foods, which are dominated by carbohydrates, high fiber, low fat, or they're animal-based foods that are very low carbohydrate, high protein, high fat. But there's nothing in that middle zone. There's nothing that's really there. And a couple of people were saying, well, it must be like nuts and seeds and things like that are there. And then we were rewarded to try and find those. But actually, that doesn't fit. Because if you look at the composition of those, they actually have much more fat than the optimal region. And it turns out that there's only one food that fits that profile. You know what it is?
Nope.
Breast milk.
Oh, interesting.
Yeah. So what I think is a potential explanation of what's going on there is when you're an infant, you need to be rewarded for eating that milk. Okay, so that when an infant eats that, it lights up all bits of the brain and they think, oh, that's nice. I need to do that again and I need to get some more of that. Once you wean, and you imagine weaning into an environment 10,000 years ago, those foods don't exist. So there's no system in place to delete that reward because it doesn't matter because you never find food that has that composition. So you never get inappropriately rewarded. And so that system just sits there from our childhood. It's there for a reason. But then now in modern society, we have like breast milk foods.
Yeah. We invented just this macronutrient profile. Yeah.
We invented foods that mimic breast milk in the composition, and we love them. And we, food companies know we love them because we buy lots of the products. I don't buy into the kind of, the big bad food company that's doing it. I think they just make products that, by trial and error, they find out people like them and people buy them. So they make more of them because their motivation is making money.
Yep.
I don't think they have a plan that they're going to make those foods and that's going to make everybody unhappy.
They just discovered this through an iterative process.
Right. And so what happens then is we're kind of dropped into this situation where we're rewarded in our brains for eating that food. and that leads to, potential overconsumption of those food types.
So you did your guys' experiments in rodents, so that that's a caveat. But assuming that directionally these things are true for humans, what you're basically saying is, if your goal is fat loss and to lose weight, you want to avoid that sort of middle ground where you've got 40 to 60% of your calories coming from fat. You either want to turn down the fat or turn down the carbs. But when you're in that middle zone, that's the danger zone for gaining fat.
And if you look at all the people who are online who are big advocates for low carb diet, that's basically what they've done. They've got fat sitting on the top of that mountain, and they've come off it by going to a low carb diet. And I think, the interesting phenomenon there is that it seems that, when you come off that peak, there are different effects. So it seems that people who come off it on low carb report that they're not as hungry as people that come off it in the opposite direction. So whether that's actually true or not, I'm not sure, but that's definitely reported anecdotally, and that's maybe something to kind of look up.
Interesting. Well, John, I know that you don't have too much time. Is there anything you want to reiterate from what we talked about, or any final thoughts you want to leave people with about this general area?
I think we covered most of the stuff that I've worked on, particularly in connection with obesity. I think one aspect of my work has been that, the things that turn out to be important are sometimes surprising things that we don't expect. So this BMR effect was not expected. Nobody had previously predicted it would be important, but it could potentially turn out to be important. So I think the key is just having an open mind about stuff. If there's probably lots and lots of things in this field that we don't know about, and it's a bit crazy being very dogmatic about it. That this is the cause and this is the solution and this is what we should do. I think the basic situation is we're not really clear what the cause is, and we're definitely not really clear what the solution is.
And for the health and metabolism nerds out there who want to measure their own energy expenditure, what was the name of that company that has the doubly labeled water?
Yeah, so that company is called Calorify. It's in California, based in California. I don't have any association with it, so I'm not endorsing the products. But if you do want to get easy access to this technique, that's the only commercial venture that you can go to.
All right. Well, Dr. John Speakman, thank you for your time.
Thank you for inviting me. I really enjoyed chatting about this stuff.